Hi, welcome back to another round of statistics. Thank you for joining me. Now, today we're going to go over section 4.3, which is complements and conditional probability. Typically it includes Bayes' theorem, but for our class here, we're not going to be going over Bayes' theorem. Now, we want to actually go through and define one terminology before we start, and that's going to be the complement. Typically, when we look at the complement, we're looking at the amount of items or the data values that are not contained in the set that we want, right? So in other words, stats-wise, it's the complement that we're looking for, all right? Some people like to think of it as like the opposite and such, but you need to develop what is the sample space that you initially want to observe. All right. Now, one of the most important aspects for complements is this note right here. This note actually lets us know what we want whenever we start looking at probabilities. Now, to illustrate this, we're going to look at the example. The example says, let's say that for the next 7 days, the probability of rain is 5%. Assume the chance of rain each day is independent. What is the probability that it rains at least one day? So as I'm looking at this probability problem, I see that they give us this phrasing right here that says at least one day over the next 7 days. Now, because they're telling us at least one day, then that means we're going to be able to use the rule of complements. But if we do this, like this says, ridiculously long way, then we're going to have to do Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. All right, so let's start looking at this. Let's say it rains on Sunday, and then it doesn't rain the other days of the week. All right, there we go. Awesome. That is one possibility. What about another possibility? Could it rain on Sunday, rain on Monday, and then not rain the other days? Sure. What about rain on Sunday, on Monday, on Tuesday? Oops, excuse me here. Technical difficulties. But then it doesn't rain the rest of the day of the week. Now, we can keep going for a long time here. All right, so we can be going for a very long time, and the fact of the matter is that there's going to be too many possibilities. All right, so we're going to have many possibilities here. Now, if we wanted to and if we had the time, we could definitely go out and list all of these probabilities and then find out of all of those possibilities, how many of those possibilities contain that it will rain at least one day within all those possibilities. So, needless to say, again, long, tiresome process. However, if we come over here and we do it more of the sane way, right, what we're going to do is we're going to label the events. The event that we want is that at least one day that it rains. Now, the complement is this event not happening. Well, if it's going to rain at least one day, what's a complement of that? Now, according to the process that we have up here, it should be that there are no days of rain. So if we take this approach where we want to look at the probability of at least one rainy day, then we get 1 minus the probability of none. But the big question is, what is the probability of none for those 7 days? All right, so now we have to go through that probability. So going through that probability is actually not as bad once we actually have this in play. So if the probability of it raining is 5% for every single day, so probability of, let's say, rain, this is this is 0.05. So the probability of no rain should be 0.95. Now, how many of these days do we want to occur? Well, we want all 7 of these days. So all 7 of these days, then that's going to be 1 minus 0.95 to the power of 7. Now, when we do this, we can then just go ahead and easily find this probability on our calculator. So here I have the calculator, and we're going to go through and say, okay, that's going to be 1 minus 0.95 raised to the power of 7. So 1 minus 0.095 raised to the power of 7. I'm going to go ahead and hit enter at this point in time, and we get this numerical value. 0.30166. All right, awesome. So now having that answer, I can then say the probability will be approximately 0.302. Great. So again, it seems that we have a very tedious way, but then it also seems that there's an easy way to do this, and we want to use that easy way to do this. Now, for the next question we're going to get that a bag contains an assortment of Jolly Ranchers. Specifically, there are 5 apple, 8 watermelon, 10 cherry, and 15 grape flavored candies. You get to randomly select 3 candies without replacement. All right, so really quickly, one of the big items here is that we're going to do this without replacement. All right, that's going to be an important part here. And the other important part is that we're selecting 3 candies. So then find the probability of getting at least 1 watermelon. All right, so I'm going to label this as A is the event where I get at least 1 watermelon. At least 1 watermelon candy. The complement of this event is that I get no watermelon candy. So this now tells me that when I'm looking at my probability here, excuse me there. So, whoa, technical difficulties, wow. You ever have one of those days where you're just trying to zoom by and then all of a sudden just, let me see, can I recenter this? Nope. A little bit more. I think I was at about 125 magnification here. And let's see if it'll do it now. All right. Nice. Okay. It looks kind of weird, but you know what? We're going to push through it. All right. So here we go. So I want to find the probability of at least 1 watermelon. That's going to be my probability of what I defined as A. And this is going to be 1 minus the probability of its complement. And its complement is that we select no watermelon candy. Now for us, it's going to be kind of nice to look at this. So let's look at without replacement. This means that when we take a candy out, we are not putting it back. Therefore, this probability is going to be dependent. All right. Now, we can go through and we can say, hey, the dependency of this, you know, can we use the rule for cumbersome calculations? Yes, we can. So, let's see. Probability of not selecting a watermelon candy. So, initially, how many watermelon candies do we have? Well, we have 5, 8, that makes 13, plus 10, that makes 23, plus 15, that should make 38. So out of these 38 candies, how many are not watermelon? All right, well, there's 8 watermelons, so 38 minus 8, 30 candies are not watermelon. After our initial selection goes down by 1, but then the selection of no watermelon candy goes down as well because we took 1 that was not a watermelon. So that means we have 29 that we can select. Then after that, it's going to be 28 out of, you guessed it, 36. Nice. So now we want to make sure that we get this into our calculator. So I'm going to go through and I'm going to put this into the calculator. So I'm going to put a pause in this really. There we go. And now what I want to do is I want to insert my newfound probability. So that was 1 minus, and then I'm going to multiply everything that I need to multiply here. All right. So that's going to be 30 divided by 38. Nice. All right. I'm going to close that parenthesis. Open the other parenthesis. That's going to be 29. Oops. There you go. 29 out of 37. Perfect. Close the parenthesis. Next parenthesis is going to be 28 out of 36. Great. So here is the probability that we're looking at. The probability is 0.5187, so on and so forth. So this probability that we're looking at here is approximately 0.519, that we actually get to choose 3 candies that are not watermelon. That's interesting because that's almost half of this probability. All right. Now, let's look at the next example. So the next example says that a satellite defense system has 5 independent satellites that each have a 0.92 chance of detecting a missile threat. Part A, what is the probability that at least one satellite does detect a missile threat? All right, so in here again, that key verbiage that I'm looking for, at least one. All right, so at least one of this, at least one of these. And now how many are we looking at? We're looking at 5 independent satellites. So 5 independent satellites, again, independent means that the probability does not affect, one probability happening does not affect the other probabilities happening. So let's look at this. So we want to find that the probability of at least one satellite detecting a missile threat. That means that this is going to be 1 minus the probability that none detect a threat. Well, let's look at that now. If we have a probability or a chance, a 0.92 chance of them detecting a missile, then what we can do is we can use that probability to say, well, if you have a 92 chance of happening, what is the probability of it not happening? In other words, not detecting. Probability of no detection. Oops, excuse me there. Let's go back. Oh, no. All right, so some more technical difficulties. You know what? I think the difficulties are coming whenever I press the back button. So I'm going to stop pressing that back button. All right, so here we go. The probability of no detection. So the probability of no detection is 0.08. Now we're going to use this probability. How many times are we going to use this probability? We're going to use this probability 5 times. So at this point in time, this probability, we're using this for those 5 satellites. So 1 minus 0.08 to the power of 5. All right, awesome, great. Now that we have this, we're going to go to our TI and we're going to let the TI do the rest of the work. Boom, here's your TI. So according to what we have, that's 1 minus 0.08 raised to the power of 5. There we go, exactly as I had it written. Press enter, and we get a probability of 0.9999967, so on and so forth. Wow, that's an extremely high probability. This probability, as you can definitely see, it's really, really, really close to 1, but it's not 1. All right, so the question is, what's the probability that at least one satellite does detect a missile? Again, almost 100% chance that one of them will detect a missile. And we're going to go back and write that up. All right, here we go. So this was approximately 0.9999967. And again, looking at this probability, it's way too large. I don't want to confirm and say it's 100%, but instead I want to see that it's fairly close to 100%, but we're going to leave it exactly like this. Now let's see the next question. The next question, part B, we want what's the probability that at least one satellite does not detect a missile threat. So at least one is not going to detect a missile threat. So at least one is not going to detect the missile threat. So that means that we need the probability of none. So what's the probability that at least one satellite does not detect a missile threat? So the complement of not detecting a missile threat is that they do detect a missile threat. What's the probability for detecting a missile threat? Well, that probability is actually right here. That's going to be 0.92. How many satellites do we have? We have 5 of them. So our probability is 1 minus 0.92 to the power of 5. So now we let the calculator do the work. 1 minus, that was 0.92 raised to the power of 5. Hit enter. Look at that probability. That probability is not too bad. All right, that's roughly about 34%. All right, so the probability that at least one satellite does not detect a missile, that's going to be 34%. Interesting. All right, so we're going to write that up here. Looking at this probability, I'm going to round it off to 0.341. Perfect. All right, now we're going to be looking at a conditional probability at this time. So looking at a conditional probability, the verbiage or the terminology is exactly what it says. We're going to put a condition in order for this probability to occur. And what we mean by that is we're going to be listing one event happening, and then we're going to go through, and once that event has happened, then we're going to see what is the probability of a different event occurring, given that a previous event has already occurred. We do have a formula for this. The formula that we typically use is listed here. There we are. All right. So let's go through and let's start looking at some of these examples. So this first example here says, let A be the event that today is your birthday. And B is going to be the event that your birthday is in this month. So the big question is, are the events A and B dependent? Meaning, do they depend on one another? Your answer to this should be yes. They are dependent, right? Because if today is your birthday month, then that means today's your birthday. If today is your birthday, then that means it's your birthday month. All right, these two are dependent on one another. Now, the probability of event A. So, in other words, we want the probability that today is your birthday. So, today it's only one day out of how many days of the year? 365? Yeah, under normal conditions, but this year is a very specific year. This year is a leap year, which means we don't have 365 days, we have 366 days. Nice. So at this time, it's going to be 1 out of 366 days, not 365. All right. Now, let's look at a conditional probability. All right. So a conditional probability. Here, for part C, we want the probability of event A occurring given that your birthday is in this month. So when I'm looking at this probability here, or when I'm looking at this, I'm actually looking to define what this vertical bar means. This vertical bar means given. So this probability would read as the probability of A given B. So probability of A given B is what we're looking at. Verbally, we're looking at the probability that event A, which today is your birthday, happens given that your birthday is in this month. All right, well, let's go ahead and let's start looking at that. So, how many days are in this month? Well, this month is March. I believe March has 31 days. All right, so let's look at that. Would you agree with me that if your birthday is happening this month, it's only 1 out of 31? So it's 1 out of 31. But if your birthday is happening today, wouldn't you agree that that's a probability of 1 because it's already happening today? All right, that's good. Which means here we're going to have the probability of 1 out of 31. All right, nice. So the probability of A given B. Now for the next one, for part D, probability of B given A. So probability of B given A. So the probability that your birthday is in this month, given that today is your birthday. That's interesting because it's not the exact same as the previous probability. This one here, the probability of B given A, so the probability of your birthday is this month, given that today is your birthday. So if today is your birthday, what does that mean about this month? Well, that means it's your birthday month. So the probability of probability of B given A in this particular case is 1 because, again, this probability depends on today being your birthday. All right. So now that we have this, we can now go to the following table. The following table here gives a mortality rate for passengers of the Titanic. People who survived versus people who did not survive, and then they're classified as men, women, or children. So we're going to go through and we're going to get some totals here. So let's start getting some marginals here. So 332 plus 1360, that's going to be 1692. Then we're going to have 318 plus 104, that's 422. 56 plus 53, that's going to be 109. Then we're going to add the rows, 332 plus 318 plus 56, that's going to be 706. Then 1360 plus 104 plus 53, that should be 1,517. Total, marginal total of 2,223. All right, so now that we have this, watch what I'm going to do here. I'm really quickly going to assign some variables to these events. For men, I'm going to assign the variable M. For women, the variable W. For children, the variable C. For survived, I'm going to do the variable S. And then for died, I'm going to do the variable D. So this probability here, notice they're going to give us the probability in sentence form. We then have to transfer it into mathematical notation. So we are trying to find a probability here. So a probability of randomly selecting a passenger who died given, so the probability of a passenger who died given, so there's that word given, that means a vertical bar, given that a person was a man. All right. So what we're really quickly going to look at is we're going to look at the first probability that is going to take place. And that first probability that is going to take place is this one here. The probability that the person was a man. So we then have to look at how many total men were aboard the Titanic. So how many total men were there? 1692? So out of all of these men that were on the Titanic, how many of them died? And that's the second probability that we want to observe here. How many of them died? So we're going to look at all of these values. All right, how many of those men died? That is 1,360. So this probability is 1,360 divided by 1,692. Roughly gives you an estimation of 0.804. All right. So the next example, we want to find the probability of randomly selecting a woman. All right, probability of randomly selecting a woman given that the passenger survived. All right, so probability of a woman given that the passenger survived. So again, the first thing that we have to look at here, oops, sorry about that. So the first thing that we're going to have to look at here is going to be the first probability. The first probability that they're giving me is that the passenger survived. So how many passengers survived? 706 passengers survived. So that probability is out of 706. Now, we need to look at the probability that we're concerned with. How many of those passengers were women? So women passengers that survived was 318. So this probability is 318 out of 706, which was roughly 0.450. Nice. Getting the correct probabilities, awesome. Next, find the probability that randomly selecting a survivor, given that the passenger was a child. Okay, so again, we need to look at the first given probability. The first given probability is that the passenger was a child. So, how many of these passengers were children? That's his total, which was 109. How many of those survived? All right, survived 56. Nice, so it's 56 out of 109. That means that this probability was 0.514. Now, when you give these probabilities, again, you always want to give these probabilities in fraction, decimal, and certain percentages. But at this point in time, I mean, these probabilities are good for what we're looking at. All right, so there are the probabilities that we want to see. Now, we're going to do a similar result here for the very last problem. For the very last problem, we need to find some, well, actually, we don't need to find the marginals here. They're all filled in for us. All right, so the table to the right shows the status of 200 registered college students. So what is the probability that a part-time student is female? What is the probability that a randomly selected student is part-time given that they are male? And what is the probability that a randomly selected female is a full-time student? All right, so before I fill this in, I want you to give it a shot. Give this a shot and see if you can get these probabilities. Now, I myself, I am going to fill it in, all right, but just not at this moment. Feel free to pause the video. All right, feel free to pause the video and to see what we can get here. So let's see, I'm going for the part-time. I'm going to first off label the events, part-time, full-time, female, and male. So labeling the events, that way I can write the notation. So one thing I want to stress a lot is that you need to write this notation correctly. Being able to do the calculations, that's awesome. Being able to transcribe those calculations into English statements, that's even better. But one thing is communicating math through paper, and that's the writing of it. That's what I'm looking for too. So again, please take time, pause the video, and see if you can get this yourself. All right, so I really quickly went ahead and filled in what we're looking at for the probabilities, mathematically wise. So for the first one, what's the probability that a part-time student is female? So I want you to notice there is no word here that says given. However, we can restructure that sentence to say what is the probability that a female student what's the probability of randomly selecting a female student given that they are a part-time student? So I'm looking for female given that they are part-time. Probability for B, I'm looking for the probability that a part-time student is selected given that they are male. Part C, I'm trying to find the probability given that a probability of selecting a full-time student given that they are female. So if you got these, great. If not, then I want you to put pause on the video, go through and see where you can restructure it, and then try to get these numerical values. Again, I'm looking for about 3 decimal places and get those fractions as probabilities. So again, take time, put pause on the video, and try to work it out. So here are your probabilities. So I hope you all got them. Now, this section actually ends chapter 4. So chapter 4 is not a really long chapter, but again, the information that we get sets us up for what we need. And what we need is we now need to look at probability a little bit more in depth. All right, so I hope you enjoyed section 4 too. I hope you all join me for section 5.1, which will be coming up shortly. See you next time.